Hey folks, welcome back to the system design playlist. So this is day 05 and today we are going to talk about the difference between SQL and NoSQL. One of the biggest decisions that we make while designing a system is to choose whether a relational database, which is SQL, or a non-relational database, which is actually NoSQL. So first in this discussion, we will discuss about the data model. Okay, what is exactly data model is. Then we are going to discuss about the schema. After that, we are going to talk about scalability, in which we have a horizontal scalability and vertical scaling. And then we are going to discuss about the query languages. After that, we are going to cover some more important topics like transaction support. And then we are going to see the difference based on performance. What are the use cases of SQL, when to use SQL, when to use NoSQL, then few real world examples. First, let's talk about the data model. So the data model of a database defines how the data is stored, how it is organized, and how it is related. Let's take an example of Amazon. So take an example of Amazon where you have three entity. What is an entity? These are the different tables. You have a customer entity, you have a product entity, like you have a product table, you have a table for order, you have like you provide the customer ID in the customer table. These are the attributes. You provide the customer name, you provide the email address, right? You have the product ID, you have the name, you have the price of the product, and then you have the category of the product. After that, you have the order ID, you have the customer ID, you have the product ID, and you have the order date, right? This much is clear. Now let's talk about what exactly data model is. So data model is the way we are storing the data, right? So how it is located? Like we have the customer details, right? We have the product details, and we have the order details. So what I am doing is I am making separate tables for all these. I am making a customer table, I am making a product table, and I am making an order table. Let's take it as an example of relational database. Here the customer, product, and order are nothing but these are the entity. What is an entity? Entity is the table name, right? And these are details, like you have, these are the attributes of the table. And you also provide the data type. For example, the customer ID can be integer, right? And then you are going to provide the name. Name can be a varchar, it can be a string. And then you have the email, right? It can also be a varchar. Then you have the address, it is also a type of varchar. Then we have product ID, which is integer. We have the name, which is a string. Price is also integer. We have the category, which can be boolean, right? And like let's say if a customer has placed an order or not, so I am going to provide it boolean, right? I am going to make the decision based on true and false. Now let's talk about the standard definition of data model in terms of SQL. So SQL databases use a relational data model. This is important, where the data is stored in the form of tables. What are tables? Table are also referred to as the relations. Now what are relations? Relation has rows which are tuples, and what we call tuples we also call them as record, and which represents the individual records. And columns, what we call columns, we call them as fields, we call them as attributes, which represents the attributes of those records, right? Then we have the primary key. Primary key is used to uniquely identify each record, whereas you have the foreign key. What foreign key do is it link two tables together and allow for relational queries. Now let's take an example of user management system. In this user management system, I have a user ID, I have the user name, I have the email. This is actually the user table. So this is a user table and this is a order table. We have the email, right? We have the age. So here the user ID is integer. Here the name is of type string, which is varchar. Here email is of type string, which is varchar. Age is of type integer. You have another table which is named as order table, where you have the order ID, you have the user ID. Here this is very important. This is called as foreign key. This is actually reference to the primary key of this table, which is the user ID. Here we call it as foreign key, right? So with two tables, users and orders, the user table contains the user details, order table stores the order details and link to a specific user. Here you have like product details, you have, for example, laptop, smartphone, headphones, and the price. What I am trying to say is, here the user ID in the orders table is actually the foreign key that references the user table, right? Which establish a relationship between user and their order. By knowing the user ID itself, you can know the order ID and you can know all the details of the order made by a user. This structured approach is ideal for applications which require complex queries. You have join operations. We have different kind of join operations like pull outer join, left outer join, and you have right outer join. Now let's talk about NoSQL in terms of data model. So NoSQL databases use flexible, non-relational data models, allowing for various ways of storing and managing data. In previous one, there was a relational model. So we were just having one method of table, which was consist of rows and columns. Here we have four methods. First, we have the key value model. For example, you have Redis. Then we have the document model. For example, MongoDB. Then we have the column family model. We have Cassandra. And then lastly, we have the graph model. You have example of Neo4j. Now let's first talk about key value model in NoSQL. So let's take an example of Redis. The key value model is the simplest NoSQL model where the data is stored as the key value pairs. This model works well for applications which need fast lookups by the help of a unique key. Let's further talk about the key value model. So let's take an example of the same user model. We have the user management system. So we have the user data. Here the user data can be stored as key value pairs, where the key is used, the user ID is the key. Here also the user ID is the key and the value is associated, which is the user information, right? Suppose this is the key, this is the key. You have a certain value. What is the value? You have the name of the user, which is John. You have the email of the user, which is the email ID, and you have the age of the user. And then we have a key 2, where the value is the name, and we have the email, and then we have the age. So this is a different format. This is the different way of representing the same data model. Now let's talk about the document model. Let's take an example of MongoDB here. In the document model, the data is stored as document. In formats, you have JSON, you have binary JSON. So each document contains a unique identifier. What is the unique identifier? It is the key actually. So it is a set of key value pairs. What we call a set of key value pairs, it is actually the attributes. So documents can have varying structures, making the document model schema-less or flexible. Let's look at the example of the user management system. Okay, so we have a ID of the user. We have the name of the user. This is a JSON format. I hope you understand this. This is a JSON format. We have the email of the user. Then we have the age of the user. So we have array of orders. Here the user John has order ID 101, and on order ID 101 he has bought a laptop which worth 1200, and here we have order ID 104 which is associated with the same user John, who has bought a product which is a smartphone and it worth around 800. This is how the document model works. Now let's talk about the third one, which is column friendly model, column family model. For example, you have Cassandra. In the column family model, data is organized into rows and columns, as like we have discussed about the relational model. But unlike the relational model, each row can have variable number of columns. So you have this row, suppose this is row 1 and suppose this is row 2. Here you have 3 columns, but here you have actually the 4 columns. You have some data here, you have some data here, here as well, right? You have variable column. This is important. You have variable column. So it is optimized for fast querying and large scale distributed storage. If I further talk about the column friendly model, let's take the same example of Cassandra. This is actually the column family user activity. Now let's assume we are building a user activity tracking system. Remember, we are building a user activity tracking system which stores the actions which user take on a website, right? What user do is user views the page, user go to the page and make some purchases for the products. Each user has a unique user ID. This is the unique user ID. You have 1, you have 2, you have 3. These are all different. And their activity. For example, you have page views and purchases, which is stored in a column family. Here you have page 1, here you have page 2, then you have purchase. These are actually the attributes, right? So on page 1, user has viewed the home page. On page 1, user 2 has viewed the home page, right? Now see, here we have actually 4 columns. Here we only have the 3 columns, right? Because user has not done the next purchase, which is purchase 2. Here the user has viewed only products page but has not viewed the second page, and user has bought a headphone worth $150, right? But user has not made any second purchase, so these are empty, right? So these are variable. Here you can see we have 4 columns, here we have 3 only, and here we have 2. Now let's talk about the graph model. For example, Neo4j. So in graph model, the data is stored as nodes, edges, and properties. This model is ideal for applications where data relationships are complex and highly interconnected. For example, you have social networks. So let's take the same example of the user management system, right? In the user management system, the user can be represented as node. The user can be represented as a node, right? We have already discussed what a node is. And a relationship between them, for example, there can be a relationship of friendship. It can be a relationship like user makes an order. So there is a relationship between the user and order, right? These can be represented as edges. So here the make is actually the edge, which is showing the relationship. Let's talk about it more well. Here you have the nodes, which is actually the users and the order. User has placed an order. User has actually placed order, which goes to the like, this is one table, this is second one. So you place an order. These are the nodes and this is actually the edge, right? The one which is showing the relationship is edge, and the nodes are actually the entity, the table which we have in relational schema. Now if I talk about more examples, there is a user John who places an order and purchases laptop. There is an user Mike who places an order, purchases a smartphone. Now let's talk about schema. What do you understand by schema? So a database schema defines how the data is organized within a relational database, which is inclusive of all the logical constraints. Now, if I talk about what is logical constraints, so you have heard about the table name, which is the entity name. You have the field. What is the field? It is actually the column. And we have different types of data types. We have the relationship between these entities. Schemas commonly use visual representations. What is visual representations? It actually uses a model, right, to communicate the architecture of the database, becoming the foundation of an organization's data management discipline. So this is actually the foundation. First we design the schema, and then we do the all the managing queries in the database. So this process of database schema design is also known as data modeling. When we design a schema, this is actually known as data modeling. This is actually the data modeling. Now let's talk about the SQL schema. So in SQL schema, the data must be defined, the schema must be defined upfront. What do you mean by upfront? It must be defined before inserting any data. So in SQL, the schema must be defined before inserting any data. Each table has a specific set of columns with defined data types, constraints, and relationship. The database enforces this schema, ensuring that every row adheres to the predefined structure. So the schema enforcement ensures data integrity. It ensures data integrity, and also this makes SQL databases ideal for applications where you need consistency. It is ideal for consistent results and accuracy as well. So this rigidity can make it challenging to adapt the changing requirements. Let's take an example of SQL schema. So you have user and orders table in SQL, right? Here is a table. You have SQL query for making a user table. This is actually the table name. This is a create table command, right? Here you have attribute, which is user ID. And you have the data type, which is integer. Another constraint you have primary key. You set this as a primary key, which is uniquely identified. And then you have a name attribute, which is actually a string, and varchar, which allow up to 100 character, right? This is the length. And another one, which is same, it is also a string, which is email, which is a varchar, which allow up to 100 characters. Then you have integer, which is age. If I talk about this another table, which is orders table, you have the order ID, same, and then you have the user ID, you have the product, which is varchar, you have the price, and then you have a foreign key mapping. Here the user ID, which is the primary key of the user table, is foreign key here in the orders table, right? And you reference user based on user ID from the user key, from the user table to the order table. I hope you got my point. Now let's talk about this example more well. Like if you need to add a new column, if you want to add a new column in SQL query, or modify a data type, or you need to change the relationship, it often requires schema migrations, right? This can lead to a downtime. What is a downtime? Downtime when your server is unresponsive. Careful planning in the production. If you need careful planning in the production system to avoid any disruption, you should not do this. Let's take an example. For example, you are doing adding a new column in the SQL. Here you run the alter table command. You have the user, which is the table name. Then you do add column. To add a new column, here you have the new column name, which is the address and the data type and the length up to 255. So this operation modifies the schema to include an address field. Every record will need to be updated and the default values may be necessary for the existing data. Now, I hope you got this. What we are doing is we are like for updating a particular column, we are updating the entire record. We are updating all the rows. Which is very time taking. So this in result causes a downtime because our server becomes unresponsive. Now let's talk about the schema in terms of NoSQL. So in NoSQL database, there is no fixed schema that must be defined. So there is no fixed schema. This is first important point. Also, this allows flexible and dynamic data structures where different records can have different attributes. So here you have different records. Here different records can have different attributes. So this flexibility makes NoSQL databases suitable for those applications where data formats may evolve over the time, right? In NoSQL databases, schema changes are much simpler because the schema is dynamic. Here the schema is actually dynamic. You can add new fields to individual records without affecting the other records. So this is very important. You can do the addition of new columns without affecting the records. Like in the previous example, what we have seen is in SQL we were adding the new column which was address, but we were affecting all the records, which was a time taking process and causing a downtime, right? Let's take an example of NoSQL. Here we have a user and orders in a document. In the previous one, the user and orders were the two separate tables. Let's take an example of MongoDB. So you have an ID of the user, you have the name of the user, you have the email of the user, and you have the age of the user. Here you define the orders, right? You have the orders in the form of array. So the order 101 is associated with the same user who has bought a laptop for 12,000 price, and there is another order with order ID 104 bought a smartphone which is a product and for the price 800. Now let's talk about another example of the NoSQL schema. In the another document, the structure can differ. So it is not always same for the schema, like it is not same for different examples. Here the structure may differ because like we have the ID, we have the name, and we have the email and the age. Here in the order, we have the order ID, we have the product, we have the price. But if I talk about the loyalty points, so we are not actually storing in the orders, right? We are separately storing the loyalty points. Whatever purchases Ron do, these loyalty points are associated with that, not for each and every order in the array. Now let's talk about scalability. What do you understand by scalability? Scalability is the capacity. Remember, it is the capacity of a system to support growth or to manage an increasing volume of work. Previously, I was doing a small workload, so I only needed a 4 GB RAM. So I only needed a CPU of 4 GB RAM or a machine. But now my workload is increased. I need a 16 GB RAM. There are two ways. Either I can do horizontal scaling or I can do vertical scaling. Vertical scaling, where I am adding the whole computation power to the same machine, and this is actually horizontal scaling, where I am using different machine where I am using multiple machine of same computing power. So when a system workload or scope rises, it should be able to maintain or even improve its performance efficiency and dependability. This is also known as scalability. So a system must be scalable in order to accommodate growing user traffic. When your user traffic is growing, when your data volumes are increasing, or your computing demand without suffering a major performance hit or necessity. Let's take in terms of SQL. Let's talk about scalability for SQL. So SQL databases are typically designed to scale vertically. These are designed to scale vertically, which is also known as the scale up. Here what I do is, like, based on the demand, when the traffic is increasing, I am increasing the storage. I am increasing the memory, which is actually the storage. I am increasing the power. So anything, whatever I am doing, I am adding to the same machine. I am just adding to the same machine, right? I am adding to the same virtual machine. Let's talk more about the scalability in terms of SQL. Like, by adding more power, in terms of power, what do we understand by power? Here power can be a CPU, it can be a RAM, right? Or it can be a storage, as we have discussed, to a single server. So here we are adding to a single server. This approach works well for moderate loads, but it becomes limiting when the application scales to high levels of traffic or data growth, because you cannot scale up. There is a limited, so it has a limit. SQL databases rely on maintaining ACID. So these basically rely on maintaining the ACID properties. What is the ACID properties? We have atomicity, consistency, isolation, durability, which makes horizontal scaling a challenging during the increasing power, because it has certain complexity of distributed transactions and joins. Now let's talk about the scalability in terms of NoSQL. So NoSQL databases are designed to do horizontal scaling. These are also known as scale out. Now what it means by scale out? Suppose this is database 1, this is 2, and this is 3. Now demand is increasing. What should I do? I cannot add more computation power to these machines only, right? What I do is, I am going to add a new machine of same power. I am going to add a new machine of same power. So this means like increasing capacity by adding more server. What you do is you add more servers of same capacity, or we can say them as nodes as well. We also call them as nodes in distributed system. So this distributed architecture allows NoSQL databases to handle massive volumes of data and high traffic loads more efficiently. Each node handles a portion of data. Each node handles a portion of data, which allow for better load distribution, and it reduces fault tolerance. Now let's talk about the query language. What is a query language? Query language is also known as data query language, or we can say database query language, which is in short DQL. It is a computer language which is used to make queries in the database. It is a language which is used to interact with the database, which is used to manage the database and information system, right? So one of the most significant difference between SQL and NoSQL database is query language itself, which is used to interact with the data. In query language, let's first talk about the structured query language, which is SQL. Structured query language is the de facto standard language which is used to interact with the relational database to perform operations such as you are doing data retrieval, you want data from the tables, you are doing insertion of data in the tables, you are updating the tables, and you are doing deletion. If I talk more about it, it is a declarative, meaning like you specify what data you want. So it is declarative. You already specify what data you want. You already specify what attributes you are adding. You have name attribute, you have address attribute, you are providing email, you are providing phone number, and then you are providing country. You are also defining the data types, such as you have integer, you have varchar, which is a string, you have boolean. So SQL allows for powerful data retrieval, aggregation, filtering, manipulation, which make it ideal for handling complex relationship between the tables in a relational database. For example, fetch user above age 25 and their orders. You are performing a select query where you want the name of the user, you want the email of the user, you want the orders of the user and the price of the products, right? There is a table, so you are performing from, because you are getting the data from the users table, you are performing join operation on the user and order table. You are performing a join operation. So here, what data you need? I need all the orders, I need all these attributes where the condition is the user age must be greater than 25. You have a condition, the user age must be greater than 25. So here the join operation combines the users and order tables based on the user ID. The where clause filters out those users whose age actually greater than 25, and the result is a list of users and their corresponding orders. Now let's talk about query language in terms of NoSQL with an example. So in a document based NoSQL database, like you have MongoDB, you have which is used for storage in JSON like formats, and MongoDB provides its own query language to query the document. While this can provide more flexibility, it also means like a steeper learning curve, potentially limitations in querying capabilities. Let's take another example of NoSQL in terms of query language. So you have to fetch users above age of 25 and what are the orders they have made. What you do is in the MongoDB query, you do database.users.find. So here is the query where the age is already provided. It is GT, which is GT stands for greater than. It is actually greater than. So all the users who are greater than 25, right? The name, the email, and the order products and order price, these all are set to true. Why? Because I need all these details. 1 means true and 0 means false. I need all these details of the user whose age is greater than 25, right? And in the same query, if I talk about the graph database, this may look like you are doing match, then you have user who has placed an order. So like we have seen that user is actually the node and order is also a node, and here the placed order is the edge. Here is also the condition same, the user age must be greater than 25 and you should return the user name, product or the price. Coming to the fifth point, now let's talk about the transaction support. What are transactions? Transactions in databases ensures that there is a series of operations which has to be executed in a reliable, consistent manner. Transactions are particularly important in applications where multiple operations must be completed together, such as you are transferring money between bank accounts and ensuring that a group of database updates either all succeed or fail. There is no inconsistency. Let's talk about SQL in terms of transaction support. So SQL databases are also known for their robust support of ACID transactions. These support ACID transactions, where let's talk about atomicity. What is atomicity? Atomicity means either the transaction will happen or it will not happen, right? Let's say you want to transfer 500 rupees. You want to transfer 500 rupees to your friend's account. So there is an interrupt. Suppose the interrupt is internet is not working, right? Now this never happens like until where the process has gone, it has transferred 250. This never happens, right? Either the 500 rupees will be credited or it will not. So a transaction is treated as a single indivisible unit. Either all operations within the transaction succeed or none of them are applied, all or nothing. If I talk about the consistency, what is consistency? Transactions take the database from one valid state to another, which maintain all predefined rules such as constraints, triggers, and data types. What do you mean by consistency? Now let's discuss. Suppose you are transferring 500 rupees and before transferring 500 rupees, you were having 1500 in your account. Now 500 you are transferring to your friend's accounts. Overall, you were and your friend was having 200 before the transaction happened. So overall, if I sum up 1500 and 2000, right? What is it? It is 3500. So before the transaction it was 35, and after the transaction as well, the sum will remain same. Only the values will change. Here you will have 1000 and here it will become 2500. So this is termed as consistency. The values are changed, but the overall amount is still the same. If I talk about isolation, multiple transactions can occur concurrently without interfering each other, ensuring that one transaction intermediate state is not visible to another transaction. So this is a parallel execution of two transactions. Let's say there is a T1 and there is transaction T2. Both are unaware of each other. These both transactions are unaware of each other. This is isolation. If I talk about durability, what do you mean by durability? Like you are storing some data, right? So it should be durable. It should stay long for a specific period of time until the machine is working properly, right? So a transaction is committed. Its results are guaranteed to persist even in the event of system crash. Even if the system is crash, the result will be in the database, right? The result will stay in the database forever. That is durability. Let's take an example of a bank transfer in SQL. You start your transaction. Now you have started your transaction. So in user A's account, you have 5000, right? Update account set balance equals to balance minus 500, right? I am transferring 500 to user B. User B has 2000 already, so it is going to sum up 500. It is the same that I am explaining. Here what you do is you do balance, which is actually 2000, and I am doing a sum up of 5 because 500 rupees are transferred from the user A to B, right? And then finally the transaction is complete. You do a commit. Commit is actually a return statement. Now let's talk about transaction support in terms of NoSQL. NoSQL databases follow the base model. SQL was following a ACID model. It is following a base model. Here B refers to basically available. What does it mean? The system guarantees availability, which means that data can always be read or written, even if some nodes in the distributed system are unavailable. It will anyhow manage other nodes to either receive the data or to provide while the retrieval. So there is a soft state. Here S stands for soft state. The system may be in a temporarily inconsistent state, but eventual consistency will be reached over the time. What is mean by eventual consistency? So over the time, the system will become consistent. Though it may not happen immediately, this trades immediate consistency for higher availability. Let's talk about a NoSQL transaction example, which is Cassandra conditional update. It is a lightweight transaction. So here we begin a transaction. What we do is we update the users. So here we set the balance. Balance is equals to balance minus 500 because we are transferring 500, right? Here we set a where condition where the user ID is A, right? So it will happen only when you have balance greater than or equal to 500 in your account. That is a constraint, right? And then we update the user set balance. Here we use set, right? We add the deducted amount to the user where the user ID is B, right? And here we apply the batch. Now let's talk about the performance. Performance in terms of SQL. So SQL databases are optimized to handle complex queries. These are optimized to handle the complex queries, which involves multiple join operations. You have either multiple joins, you have aggregation. What do you mean by aggregation? We have some aggregate functions, right? You do aggregation. Aggregate functions are like you do count, you have min, you find the minimum value, you have max. These are predefined functions. And then we have transactions. So it is very much easier to do with the help of SQL. So for small data sets, SQL databases perform well as the query optimizer can efficiently execute joins and filter out the data. As the data grows, performance may decrease, right? So data is increasing, whereas performance is decreasing. That is a drawback. Why this happens? This happens because of complexity of joining large tables, especially if indexing is not optimized. So it will go to each and every record in a table. It will go to each and every record, right? For even a single update in the column, it will reorganize all the records. So their performance can be excellent for ready heavy applications. Their performance can be excellent for ready heavy applications with well-defined schemas where data integrity is paramount. So if you already have a well-defined schema, see, we have already discussed about it. We already defined the schema. We define the attributes, what kind of data types we are going to assign, what will be the primary key, what will be the foreign key mapping, and will it be a one-to-one mapping, will it be a many-to-many mapping. We define it already in SQL. So it is good for ready heavy applications. They may struggle with write intensive operations. So these are not suitable for write intensive operations. Why these are not suitable for write intensive applications? Because when you write, it will update each and every record, it will update each and every attribute. So like it is time taking and which causes downtime. This is mainly because of improper indexing. This is mainly because of improper indexing and improper optimization of the queries. There is transaction overhead. Why this happens? Transaction overhead happens because of intensive queries, which can reduce performance when there are multiple queries executed in a single transaction. Now let's talk about the performance in terms of NoSQL. So NoSQL databases are optimized to offer high performance at scalability, especially for large volumes. These are especially designed for large volumes of unstructured or semi-structured data, either unstructured or semi-structured data. So they prioritize horizontal scaling that we have already seen. They prioritize horizontal scaling, and they are optimized for high throughput. They are also optimized for high throughput. So where there is read to write operations, making them ideal for real-time applications, big data, and large scale distributed systems. So these are especially for the large data sets where the performance remains high as the additional nodes are added to the cluster, distributing the workload. So these are for large data set. NoSQL databases are generally faster write performance. They generally have a faster write performance. If I compare to the SQL, they also offer eventual consistency. Now, what is eventual consistency? In distributed NoSQL system, data does not have to be immediately consistent across all the nodes. This reducing the need for logs and increasing write speed. It also gives denormalized data model. What do you mean by denormalized data model? NoSQL databases often store the related data together in a single document, which means you need only fewer write operations if we compare to the normalized SQL model. So here we need very fewer write operation. Finally, now let's talk about the use cases of SQL. SQL databases are ideals for certain kind of applications which require structured data. The data should be in a structured format. You have the predefined schema, you already define the attributes, you already define the type of data, and you already define the schema structure in the schema migrations, which is actually the data modeling. And if we talk about complex queries, these involves joins, aggregations, and transactions. You have a strong consistency. These follows the ACID, which means atomicity, consistency, isolation, durability. These are the very important properties of SQL. These also have relational data. So here the relationship between the table is very important, which is done using foreign key to define the relationship between two tables. If I talk about the use cases of NoSQL, NoSQL databases are ideal for those applications which require horizontal scaling to handle large amount of distributed data. These also need high performance reads and writes for real-time applications. These need flexible schema to store unstructured or semi-structured data. These are required for eventual consistency and high availability, right? If I talk about the distribution system, these should be highly available. Now, let's talk about the summary. In this module, what we have discussed about some important aspect. We have discussed about the data model, and we have discussed about the schema. We have discussed about the scalability, consistency, query language, what are the transaction support, performance, use case, scaling challenges, data integrity, joins, and the examples. We have discussed about the difference between SQL relation, NoSQL non-relations. These are the differences. You can read from here as well. These are some summary differences. So this was all about this video. I hope you like it. Do mention in the comment section if you have any doubt, if you have any kind of question. Always keep yourself engaging with the community. Do ask question in the comment sections. In the previous video, I have seen that you have not mentioned in the comments regarding the questions, regarding the doubts I was asking. So please do like, share, and subscribe my YouTube channel. Keep intact, and we'll see you in the next lecture. Thank you.